So in this part, we will be talking about the data analysis of the development for the ML. I would like to say that today's sessions are really a sequence that we need to understand in order to build our knowledge and improve our, let's say, capacity in how really we can achieve our goal, finally, to protect the consumer as the basic scope of our work. So in this session, we are going to define mainly statistically what is maximum level, or obviously their relevance to codex standards, to understand the importance of occurrence data, as we said before, to identify data distribution types, and to apply statistical methods to analyze contaminant occurrence data, especially for what we call non-parametric approaches, to handle data challenges such as low sample size, left censored data below LOD and LOQ, as well as to evaluate and compare multiple data sets, and finally to recap by using what we call the 5-step process for statistically robust ML development. So this is our agenda for today, as I said, and we will start with a quote that I liked a lot. First of all, do you know this guy, Edward Deming? Any idea? Who's... So he's one of the quality gurus. He's a statistician, and obviously what he said is very interesting. He said that in God we trust, and all others must bring data. So data are facts that we need in order to understand and in order to, let's say, clarify our status. So I believe from this quote, we can understand that it's not a, let's say, option, it's a mandate, it's a must to be able to understand what's happening through facts and evidence, which is equal to data. So already we talked about the MLs, the maximum limit, which is a regulatory upper limit for contaminants in food or feed. So this is a definition that should be based on scientific data, good practices, and risk assessment. So in order to achieve a good, let's say, level of risk assessment, we need scientific data, good practices that will generate for us what we call the ML. Obviously, we rely on the occurrence data as the evidence-based. What do we mean by occurrence data? It's the data that is basically reflecting the concentration or the amount of a contaminant in a food. Okay, this is the occurrence data. And as we said before, the food that is as much as possible close to what we eat. Okay. Why statistical analysis is important? To ensure MLs are protective, realistic, and reflect real-world contamination patterns. I believe this sentence can summarize all what we want to take as filters in our data analysis. We should always think about this. How can we make the maximum limits protective, obviously, to consumers, realistic, and this is very important because we may go to underestimate or overestimate the contamination, as well as to reflect the real world contamination. And here, Dr. Amin explained deeply, when we talk about data, we need it as much as we can, real world data, reflecting what is really coming into our plate. Obviously, there is a lot of sources that can generate data that we can use in ML. I will not go through this again because we have already talked about it before. So if we want to introduce the statistical analysis of occurrence data, we can say that statistical analysis is essential for handling occurrence data sets in the development of the maximum levels for contaminant in food and feed. So we cannot generate maximum limits without statistical analysis, as well as that this will ensure that MLs are based on robust, scientifically sound data reflecting real-world contaminant levels. And we'll see some examples how the misanalysis of the data can lead to bad decision-making on the level of risk assessment. There is steps in analysis. Obviously, we started with what Dr. Amin mentioned, data extraction and cleaning, data cleaning. So those are the two first steps that we should follow. And today, in this session, we will be tackling the distribution assessment as well as the presentation of the results. And those results, as we said, will be sent to the electronic working groups for assessment in order to prepare the risk assessment results and share it with the risk managers. For sure that our aim is to apply those maximum limits at the global level. And this is a challenge, obviously, because the level of contamination is not the same all around the world, as well as the data quality is not the same all around the world. But we need to know that globality will ensure that MLs are relevant and effective across different regions and conditions. Imagine that you will specify one number that could be applied for all parts of the world. This is not really very obvious and easy to digest. So the expert working group, as we said, they will take those results and they will work on it for informed decision-making, and they are relying on the data that we can generate in order to finalize the establishment of the maximum limits for contaminant. So as we said before, we are now talking about only contaminant, not other types of substances. I always ask this question, why statistics save lives? And maybe, as we said, sometimes we don't like to work with numbers, but sometimes really statistics can help us to differentiate between what is true and what is wrong, what is real and what is fake. And obviously, the core message is that the robust MLs, maximum limits, will lead not only to consumer protection, but also to fair trade. Who agree with me on this message? Any? No? The others? Do you agree? If you agree, raise your hand. So who can tell me how can the ML ensure fair trade? Because consumer protection, I think, is obvious. But for fair trade, how can the maximum limit can ensure fair trade between countries? Okay, we'll have a standard limit. What else? Okay, so everyone will be treated in the same level for the trade. There is no discrepancy in the levels. What else? Standardized quality and safety, obviously. So let's always think about this. Maximum limits of contaminants, it's not only related to food safety, it's also related to the fair trade. As long as this maximum limit has been defined and developed on a robust scientific basis, it will lead obviously to what we call consumer protection and fair trade wings of the main concept of our work. So our work goal is to set science-based maximum limit to minimize obviously the health risk and, as we said, for fair trade. So this is why the main objective is to minimize health risk. This is why, according to the Codex guidance, MLs should be set at a level which is slightly higher than the normal range of variation in levels in food and feed. And this is what we call worst case scenario. So when we set the ML, we push it a little bit higher to be sure that all, let's say, the result will be inside this level or limit that we are setting up. And we'll see how. So let's say if we got a result of 12.3, we always round it up to 13 or even to 15 to be sure that we were able to protect all those factors that we said. Let's now start with after Dr. Amin presented the generation of data, the extraction and the cleaning, let's move now to the assessment of the distribution. I believe some of us know about this picture or this figure where we talk about how our data is distributed, okay? What we see in the center, this is what we call the bell curve normal distribution set. So as you can see, we have here the majority part of our data set, our data numbers are in this part, which is around the mean, the median, and mode. We have few results that are lower and also few results are higher. So it's a very symmetrical distribution showing a certain normal distribution of data. And when we talk about this situation, we are talking about what we call parametric situation, which is more related to a certain way of data analysis. So if your data set is normally distributed following this shape, you will be using a certain type of statistical analysis that will be different from the two other scenarios that you can see it, where the data is not symmetrical, but deviated or deviated to higher levels. So here you can see that mean is not anymore equal to median or mode, and there is a very low part of your data that have a certain low results, and the majority part of your data is going up to high results. So you have high results in your data set. And this situation, we call it skewed, is the situation, deviated situation, where you can see that we call it negatively skewed or left skewed. Why we call it left skewed? Because we follow the tail, this part where we have the minimum number of data set that are to the close to zero. And the other side, we have what we call positively skewed or even right skewed, where it's the opposite of this one. The major part of your data set is more close to zero, very low, and a small number of your data set is high in results. To make this explanation, because this is very important, easier, I would like to ask for any voluntary person who would like to join me on the stage. Who dare? There is a prize at the end. Yes, please. So we have three situations. We have normal distribution data, negatively skewed distribution data, and positively skewed distribution data. We'd like to have the microphone, please. You have one. Oh, already you are. So I will give you three scenarios, and you will tell me which scenario is related to which situation. We have, first of all, aflatoxin levels in peanuts, fiber levels in whole wheat bread, and pH levels in pasteurized milk. So those are three scenarios. And I would like to ask you, from your point of view, which one is related to which scenario and why? Is the question clear? Okay.
I think that the aflatoxin level in peanuts is related to the symmetrical distribution.
So you are saying that aflatoxin level is related to the symmetrical level. Who agree? Who don't agree? Okay. Can you please tell us why you don't agree? If we can have the microphone, the second one.
I don't know. I thought that the pH levels in pasteurized milk was the middle one.
Okay. So the pasteurized milk is in the middle one. So you don't agree that aflatoxin level is in peanuts is in the symmetrical one?
I believe it's very hard to get an even distribution for something like that.
Okay. Do you agree? So let's come back. So let's start with the aflatoxin levels. Where you put the aflatoxin levels? Positively skewed or negatively skewed?
Positively.
Positively skewed. Why? Because the major samples results of aflatoxin level in peanuts should be close to zero. Otherwise, we will die all. Yes? And few of those samples are above, let's say, a certain level or more to the upper level. So if we come back to fiber levels in whole wheat bread,
the opposite should be negatively skewed.
Negatively skewed, because when we talk about fiber in whole wheat, we are expecting to have high level of fiber, okay, and few samples that are not really rich in fiber. And finally, pH level in pasteurized milk.
It has to be
so
constant.
the major part of the samples will be in the center, and that's the result. Thank you.
Welcome.
So if we want to summarize this short, let's say, simulation, we can see that for each case, data generated will follow a certain distribution, okay? So we cannot say that we have always the same distribution of data according to this example. So if we focus on the last one, what we call positively skewed, right skewed, this is mainly what's happening with all types of contaminants. So all types of contaminants, we know that they follow the right skewed distribution, okay? So they follow this format of the situation, whereas we said the major part of our samples will be around a lower level and few part will be up to the higher level. Are you convinced for this? Is it okay? So coming back to what we said before, we should be okay with that when we talk about contaminants, contaminants cannot follow a normal bell-shaped symmetrical distribution. Okay? They, by nature, follow a right positively skewed, right skewed distribution. And as I said before, because contaminant will not follow the symmetrical distribution, we cannot apply parametric statistical test or assessment or a certain type of test. What we apply for this situation, and we will see it later on, we call it non-parametric statistical assessment. It means there is specific tool, statistical tool to be applied in our situation. Not all tools can work, and this is very important because when we understand the shape of the distribution of our data, we can know and we can be sure that we should follow a certain, let's say, type or protocols of data analysis. So we agree that contamination data distribution is often right skewed. This is why parametric methods are not suitable because they need that the distribution should be normal, which is not the case, as you can see, and may underestimate high percentiles and may underestimate the real ML. So if you use parametric methods, you will be underestimating the real level that we should work on it. And here we will have bad decision because it's based on bad assessment. So the recommended approach is using the non-parametric methods, like what we call the empirical percentiles or fit-log normal distribution. We'll be talking about it later on. It means what? When you have a data set, okay, a series of data coming from occurrence data about your the contamination level in your product, we cannot use the normal mean, median, mode, and so on, because those are more related to normal distribution values. We need to use what we call percentile, which is more used when we have non-parametric methods. So to make the long story short, since data distribution of contamination in products is following a non-parametric shape or skewed shape, we need to use percentile instead of other methods in order to generate our MLs. Any question? Okay. So as we said, why not to use the mean or median? Because MLs must cover the upper end of contamination level, which is not really applicable for the normal distribution, because we need to be sure that we don't underestimate the real situation. This is an example why parametric method fails. So if I'm assessing the lead in spice, if I calculate the mean, it will be 0.8, for example, ppm, which is underestimating the risk. If I calculate the mean plus 2 standard deviation, it goes to 2.1. It's still missing extreme values. This is why I need to search for the percentile, which can capture the tail risk, which is related to the most critical part of my data set, and we'll see it now. So we use the percentile, mainly the 95 percentile. We'll talk about it in details, because this is the value below which 95% of the data fall. So this is the value that we can adopt as a good value to set our ML, not the mean or median or mode, since, as we said, our data set is not normally distributed, it's skewed or deviated. And in food safety, it helps to identify high-level consumers or high contamination levels if we are talking about contamination, important for exposure assessment. Because when you, as we said, we will do it every time, what is exposure assessment? Is equal to what? Occurrence times consumption. So if you lower your occurrence, you are lowering your exposure assessment and you are underestimating the risk. This is why you need an occurrence that is real, but at the same time that can cover up to 94% of the data to be sure that you are securing all types of possible scenarios. And then you will run your risk assessment to see if this level of exposure is risky or non-risky. So if we want to take this graph, which is, as we said, positively skewed graph, this is the tail where 90 to 95% of contamination data is here, the high level for contaminants. And most samples, the majority of the samples are or low or undetectable in contamination. And few have extreme contamination. And here I'm talking about this tail, Zanab, Zabatkun, that is really related to rejected from the market. And Dr. Amin will follow on this later on regarding how to calculate the rejection rate. So we can go up to 98% percentile, or we can go down to 95% percentile. And as you see here, here comes the hypothetical ML that we need to calculate. So how we calculated, obviously, I'm going to bring the two, the manual and the electronic way of calculation of 95th percentile. Let's say we have to measure a contaminant X in a matrix Y, and I got 20 samples of this product, and I measured the contaminant level. So I got, as you can see, the results. So in the sample number 1, I have 30 microgram per kilogram, and so on. The first step I should do is to put it in order. Okay, ascending order from the lowest up to the highest value. Then I use the percentile position formula, which is percentile is equal to n, which is the total number of the data set, plus 1 over 100 times 95 if I want to calculate the 95th percentile, or 98 if I want to calculate the 98th percentile. And in this case, it will lead me to this value of 19.95. What does it mean? It means that my percentile will be between the 19th and the 20th value in the sorted list. So this is the position of my 95th percentile value, okay? So here it's giving me that my percentile, which is the 95th percentile, will be between the 19th and the 20th values. So if I come back to my list, sorted list, the 19th value was the 40, and the 20 value is 41. Okay, so if I want to calculate the 95th percentile, I will go for this formula without going more in details, because nowadays we use electronic way, and it will lead to a 40.95 microgram per kilogram as the 95th percentile. And as we said, based on Codex guidance, and in order to go to the worst case scenario, we round up this value or to 41, or even we can go to 45. It depends on our assessment and our study at this level. And let's say that percentiles help avoid underestimating risks. As we said, it's used by all types of bodies who works on it as the one that is really used to reflect, first of all, realistic, but also worst case scenarios. Okay, any question? When there is no question, it could be in the two, yes. But we need to calculate the mean. Yeah, we can do it. I didn't, but we can have the result after, and we can compare, obviously. But obviously, it will not, it will be somewhere in the center. So 28, let's say 29, okay? So you are pushing the worst case scenario in a lower case scenario, which is not good, because you need to check what is the maximum exposure that we are exposed based on the contaminant. Okay. For those who are expert in Excel, there is a simple Excel equation that you can use to calculate the percentile. So if you have a set of data, you put equal percentile point EXC, and you select the row of your data and come out 0.25 if you want to use the 25th percentile, and you got directly, electronically, the calculation of the 29th percentile. Let's move now to answer this question. What is the minimum number of data points to obtain percentiles values in order to generate MLs? How many data set do we need? How many data points do we need in order to generate the 29th or the percentiles in general? Any idea? 3? 20? مين بيزيد؟ 60? 100 because it's percentile? Okay. 1,000? Do you want? High number. Unlimited number. As long... Okay. Any other... Okay. Obviously, there is an answer to this question, and it's based on a complicated formula that will be used in order to generate the exact number of samples to be tested in order to be able to generate. And what we call exact number is a minimum number of data set. First of all, let's say that the number of samples that we need depends on the confidence level that we would like to work on, which is mainly in food safety as used as 95%. It means I want to be sure that my result is true up to 95%, and I accept an error of 5%. This is commonly used at level of confidence. This is first. Second, as we said, in order to specify the number of samples that we want to test, we need to specify the percentile that we would like to work on. And as we said, 95th percentile is the most usable one. So it's easy to memorize this because we are still in the 95th percentile, 95%. So we want to know the confidence level, and we want to know the percentile level that we want to work on. And let's make it easy. Those are the levels that are mostly adopted worldwide. And this will generate a minimum of 59 data points that is necessary as a number to estimate the 29th percentile with 95% confidence, ensuring statistical robustness. So 95%, 95th percentile will lead to a minimum number of 59 data points that will allow me to start to analyze and search for my value for ML. And obviously, if I have less data points, it's not the end of the world. There is other tools to be used in order to generate those numbers. But obviously, in normal situation, and what we need to know is mainly at this level. And just to show you other scenarios, so as you can see, the minimum number of data points is based on the level of percentile and the level of confidence that we would like to do. Let's have a look, first of all, on the first case, the option 1. For a confidence level of 95% and a 95th percentile to be calculated, as we said, we need 59 data points. If I increase my confidence level from 95% to 99%, so it's really close to 100%, obviously the number of data points will be 90, so almost the double. So I need to double my number of samples if I want to go up to 99% of confidence level. And as you can see, the more I go in the percentile level, the number of samples needed will be higher. Obviously, the same here. How about if I don't have a confidence level to be estimated? Obviously, in this case, numbers will increase and increase up to 400 data set to be used in order to generate a let's say, ML based on the 95th percentile and this. So this is why when we are talking about 59 data points is needed, which is the minimum number that we need based on this, let's say, condition, 95th percentile and 95% of confidence level. If we don't have 59, what should we do? So to handle data set with lower number of data points, in general, when the JECFA evaluation suggests that a health risk from exposure to a contaminant is significant, we can accept a smaller number of data points than the minimum number that we mentioned here. So between tackling a significant health risk we can compromise with the lower number of data points. So when an ML is urgently needed for consumer health protection, when we have an emerging urgent situation, the electronic working group tasked with recommending MLs should consider recommending to the CCF the development of MLs, even if the number of the data points available is not too high, it's a small number. And if sufficient data later on become available in the future, we can revise the ML that we put it, and we can update it accordingly. Obviously, if there is no immediate health risk, we should wait until we got additional data calls to fulfill the minimum number of data set before we launch our assessment. Okay? So safety first. What about left censored data in dataset? Any idea what do we mean by left censored data? Yes? What do we mean by left censored data? Most of the results are high, are positive. Not. Yes, that's it. So left censored data is more about non-quantifiable data, okay? So it's values that are or below the LOD or below the LOQ. So we don't have numbers in our data set when the major part of our data set is not a quantifiable numbers. So we just put less than 1.0 or less than our ND not detectable. Okay, this is what we call the left censored data. And in this case, obviously, we need to have statistical analysis, but we are limited because I need number. I cannot put less than. I need a certain number. In this case, obviously, we cannot ignore this data set. We cannot say, since we don't have real numbers, we will put it aside. No, this will bias the analysis. The substitution methods are employed to assign value for these data points. So it means what? It means whenever you don't have a quantifiable data set, so it's an ND not detectable or less than 1.0, we need to transform this descriptive result into a quantitative result, into a value that we should insert it instead of this value. So this is what we call substitution method. We are substituting a qualitative result, not detectable less than, to quantitative result. And in this case, the common substitution scenarios are the lower bound, LB, the middle bound, MB, or the upper bound, UB, which is more related to the LOQ. That I'm going to explain it now. So the first scenario is lower bound scenario. What do we mean by this? In this scenario, results below the LOQ are replaced by 0. So every time you have a result less than LOQ, you will transform it into 0, or by the LOD if the LOD is known. Obviously, if the result is higher than the LOD are replaced by here the 0. This is the scenario 2 is the upper bound scenario. Result below the LOQ are replaced by the reported LOQ value. So I moved from less than LOQ to the LOQ. Okay, I changed from qualitative less than to the minimum value of the LOQ. And the third scenario, which is what we call the middle bound scenario, a point estimate between two extreme scenarios, and this is the case, assigning a value of LOQ over 2. So the half of the LOQ or square root of the LOQ or LOQ plus LOD over 2 if the LOD is known for the analytical results below the reported LOQ. And let's say also the most usable situation is to use LOQ over 2 is the most widely used in dietary exposure assessment. So obviously, we don't have enough time to go in deep in this, but you will be working on something that is similar during the breakout sessions. Let's say that no data is not usable. Even if the data is not quantifiable, we can change it to a quantifiable using one of those, obviously, scenarios. So for each of these scenarios, if the LOQ is not reported and only the LOD is reported, so we use the LOD as an alternative. Okay, so to sum up, if my data set is a left-censored data set, it means it includes a lot of less than to a certain value, not detectable, and so on. There is 3 scenarios to follow. You can choose one of. Basically, the middle bound scenario is a point estimate between the 2 extremes, and in which you can or use LOQ over 2, where there is no value, so you substitute it with this, or the other situations. Attention. If and when we have a set of data that are too close to each other and are also close to the reported LOQ, it means when your data set includes values that are homogeneous, so too close to each other, and they are all close to the LOQ, the limit of quantification. In this case, developing an ML may be unnecessary unless the contamination or the contaminant is highly toxic. So the electronic working group can make a recommendation to CCCF on the appropriateness of an ML in this situation. So there is some cases where we don't need to set an ML because our data and the occurrence data show us that there is a certain consistency in the values. They are really close, and all values tend to be near the LOQ. So there is no need to really make this case, but obviously this should be assessed case by case without any, let's say, previous assumption on this. Okay, we move now to talk about combining and comparing data sets, multiple data sets. We know, obviously, that we want to have a global applicability of Codex ML. And when we say global applicability, it means what? It means that we need to get information, data set from different countries, okay, and not from one country as it is. This global applicability needs to have data from regional and from areas where we can have a certain variation. And those data sets may vary by region or years, where we need to compare the data set. What do we mean by this? Simple example. If you want to generate a combined data set, including data coming from different countries, you cannot do it before verifying if those data sets are similar, because you cannot mix oil and water. So if I have data set coming from, let's say, from Oman and data set coming from Qatar, can I say directly I can put all together and generate one ML based on this data set? No, because maybe there is what we call a statistical difference, significant difference between the two data sets. And when the data sets are not statistically similar, I cannot combine the data set. Okay, so before you combine any two data sets coming from two countries, you should be sure that those data sets are statistically not different. Is it clear, this idea? And I think it's obvious for everyone. I cannot assume that all data sets are similar. And if I want to make what we call a multiple data set, I need, first of all, as a prerequisite, to verify that my data set is really statistically similar from the different components. Yes? No, when you generate your data from country A and country B, before you combine the two for global assessment of ML, you should verify that those data sets are comparable, are similar statistically. Okay, so I'm not talking about they have the same numbers. I'm talking about that you can combine. So you need to verify that the two are water to mix or the two are oil to mix. But if you find that one is water and one is oil, you cannot mix it together. So there is a prerequisite before we combine several data sets to use statistical analysis in order to achieve this homogeneity in the final global data set. And in order to do this, there is statistical tests that we use. Those tests are, I will bring you back to the first part of my presentation. Those tests are related to the shape of the distribution. So if your data is normally distributed, you use parametric test. And if your data, as our case, is not normally distributed, is skewed, is deviated, okay, is the contaminant are positively skewed or negatively skewed? The data set positively. Okay, so why? Because in this case, we have the major part of our data set is close to low, and this low part of the data set is close to high. In this case, also not to complicate things, we use non-parametric tests, okay? Such as Mann-Whitney test, excuse me, Mann-Whitney test. If I have to compare two data sets, one from Qatar and one from, let's say, Oman, or Kruskal-Wallis H test, which is a test used if you want to compare more than two data sets, okay? And this will help to assess distribution similarities. It means it will help me to say, can I combine or I need to assess it individually? Do you agree? And this is basically based on, for those who are familiar with the hypothesis, the null hypothesis, which is the hypothesis zero, stating that all data sets are coming from the same population or they are similar. Okay, so if I have two data sets, I cannot merge it directly. First of all, I need to check their similarity, if they are similar, or if I'm allowed to mix. And how can I do it? By statistical tests like the Mann-Whitney test, if I have two data sets, or the Kruskal-Wallis test that I can use if I have more than two data sets. And in this case, I check the p-value of the test, okay? And if the p-value is lower than 0.05, I can refuse the null hypothesis. It means the data set are different. And if this value is higher than 0.05, I can accept or retain the null hypothesis, stating that there is no statistical difference between the two data sets, so I can combine. In order to make it simpler, because obviously we are not here to go in details on this, I will take an example of checking aflatoxin in peanuts. I have two data sets, okay? 40 inputs coming from Nigeria and 40 inputs coming from Argentina. I have, as you can see, the country and the aflatoxin level, total aflatoxin in ppb, as well as the sampling date and the sampling source. I have a set for Nigeria and later on a set for Argentina. I will show you as a demonstration how can we do this using a software, statistical software named SPSS. So just as the demonstration to show you how can I answer my question. Can I combine the two data sets? Yes or no? This is our object. So as I said, we have here the data set. As you can see, we have Nigeria data set and then Argentina, okay? And you have a data point for each one. So what should I do? I have a data set showing a country, the values, the sampling date, and the sampling source. Some samples were taken from open market, from warehouse, from rural farm, and so on. So I go to analyze, I go to non-parametric test, as we said, because we know that contamination follow what we call the non-parametric type. And here, if it's not clear, I can use the other. No. I think this is better because, okay. So I go to analyze non-parametric test, and I go to independent samples because I have two samples to work on. And here I will choose to test what? I want to see for aflatoxin level, if the levels of aflatoxin are, let's say, can be comparable between the two countries. So I take the country and I put it as groups, as if I am saying what? I'm saying I want you as a software to compare the two countries regarding the aflatoxin level, trying to see if I can merge or not my two data sets. But before I do this, I need to run a check before this. Who can tell me what should I check before I run the test? What should I check in my data set? So I close this. What should I check? Yes? Confidence data? Level, no. Huh? Outliers, as Dr. Amin mentioned. My data set should be cleaned and verified that I can use it, because outliers, as Dr. Amin mentioned, will bias the assessment itself. Okay, so before I go in this, I need to see if my data set includes outlier or not. Okay, so rapidly to show you how we can do it and to apply what Dr. Amin mentioned, we go to analyze to descriptive statistic explore. Okay, excuse me. Oh. I will choose my aflatoxin level, okay, and I will say okay. And I will check the result by looking at the box plot, this one. Do we have an outlier, yes or no? Do you see the outlier? Where is the outlier? Number 12. So this assessment is saying to me that pay attention, you have one value that could bias your analysis, that is number 12. And this is very important. In this case, what I should do, I should go back to my data set and look at the number 12, which is this value. So the sample number NG012, Nigeria, which is 29, is considered as an outlier. So I should remove it. Otherwise, it will affect, obviously, my assessment. So let's say, because I put it just for this, let's say it's 22, it's not 29, because this is what the case. So let's come back. So after cleaning my data set, okay, by removing this situation, again, I go and analyze my, as we said, my data set by including the aflatoxin level in the test field and the country in the group field, and I will say run. And here comes the result. If you look at the result, you can see that the test that we conducted is the Mann-Whitney U test, okay, showing a significance, or the p-value is 0.58. This value is higher than 0.05. It means the null hypothesis was retained. We keep it. And the null hypothesis say that there is no statistical difference between the two data sets, so I can merge and generate my ML. So in this case, I can, as we said, be sure statistically that my two data sets are statistically similar. So I'm allowed now to merge those two sets and generate my ML accordingly. Obviously, in this presentation, also you can see the nice distribution of my results accordingly, and I can have the different data set results statistical without further discussion on this. Okay, so it was just an example to say that obviously, whenever you have two data sets or even more, because Kruskal-Wallis test can be used for even more than two, we are sure that we can use or not to merge between, to combine the different, let's say, data set accordingly. So this is an example when you have individual data set and combined data set, and those data set coming from statistically same, let's say, sources. So as you can see, it's relevant and it's more or less the same input. To speed up and to summarize also, obviously, when your data sets are not comparable, when the statistical results show you that you are not allowed to, let's say, to merge, you are obliged, obviously, to run your analysis individually, each data set alone. Finally, as we said, just to recap what we mentioned, the statistical analysis steps are the following: clean and verify the data set, what we have learned with Dr. Amin and what I show you in the checking of the outlier, among others. Assess the distribution of the data to be sure that it's not normally distributed, it's skewed positively. Use appropriate statistical method like this one, or obviously others, to generate and estimate the percentiles. And we agreed on the 95th percentile to cover the status of worst case scenario, and obviously round it up to a reasonable ML. So as we mentioned before. So as a take-home messages, based on all what we mentioned, to develop MLs using statistically robust data set, prioritizing, minimum data requirement and appropriate distribution assessment. So we need to have a minimum number of 59, and we need to be sure that the distribution is appropriate for the data set. Obviously, statistical tests should be used. We cannot do it just by calculating mean, median, and so on, because it will underestimate the real exposure. Sometimes we need to go case by case to decide how to, let's say, to develop the MLs, as we said. Obviously, we should use transparent documentation practice by using softwares, data results, obviously, this is very important. And finally, we should always think about the skewed data. That is the case of contaminant, by applying the non-parametric test and all other methods. My last message is the following. I asked the AI to generate for me a picture, okay, that summarizes all what we discussed. He gave me this funny one. So the first one is asking, I think this looks safe enough. And the other one is saying, let's ask the 29th percentile. But there is an error in this picture. Who can tell me where the error? The graph. It's a normal distribution, but in our case, it should be skewed. So pay attention to AI because even AI can be wrong. Thank you.